Okay, thanks very much everyone. Welcome. Glad you could join me. Just about to get underway with our recording for Math Mod 2, and we're doing a split dual purpose thing today, so that's going to be a bit of fun, isn't it? Alright, so just let me know you're there by giving me a hello on the chat. That would be great, and we'll get started. Okay. It's a great time, isn't it? We've got so much on and we're getting through our work. Public holiday tomorrow, so that's the reason for the change to the format. We've got a little bit to get through tonight, so hopefully we'll get through all of that fairly readily. Certainly I don't think I'll be concerned, but welcome to everybody that's come along. And I understand that so look, what we'll do is with questions around MTs, I'll leave it till the very end if that's alright. So we'll do the MTs at the very end, but for simple things like that, all you've got to do is take a photo and send it to me. You know, we'll deal with that in a different time, at a different place. Remember the know-how sessions on a Tuesday night, but send me a request to review your paper, because I've got logs, I know everything that you did, so there's no problem with that. Okay, so now, like I said, I want to move off the schedule, but if you look at the schedule, I said to students quite a bit, look at the schedule. I've posted a refreshed online, and the information, it's all there synced, and it's all there correctly. So please look at the outline. Look at the outline, look at the outline. I find that students are not going to read the file. Not all of you, so don't feel as though I'm rousing on all of you. That's not the case. There's a couple of you who are not reading the information as it's coming up each week on the Monday morning, or looking at the subject outline. I did a lot of work to get that sorted out very quickly for you all, so we just need to follow that. Okay, so let's move on. Today we have a look at Poisson distribution. Now, it's a funny pronunciation, this one. It's Poisson. So it's like pois. There's not an Australian equivalent to this, so pois is about as close as it gets. Okay. But it's a P distribution, a Poisson distribution. So we'll learn a little bit about that tonight, and do a couple of hand calculations, and then we'll move on and do the other part, which is the maths part. So random variables of Poisson type are used to model the number of events that occur over time. So it's a counting one. Now there's an equivalent exponential one. It's not an equivalent, but it's like a partner. So this one does the count, the number of events that occur over time. The exponential does the interval. So if you can write that down, that'd be good. So this one does the count, exponential does the interval. The number of events that may occur may be an integer or greater equal to 0. Okay. A random variable x is the number of times that a specified event occurs over some unit of measurement, time, distance or area, the probability that an event occurs in a given unit for that particular thing. Alright, so let's have a look at what the Poisson distribution looks like. To describe the Poisson distribution, we define a parameter. Now, that's the Greek symbol, okay, lambda, which is positive. This means in math speak, this is a very good math speak. Sorry, I'm just going to press another button here. In math speak, this is a very good way to write. So we've got lambda greater than 0. The way that you would read that in mathematics is that you would understand that to mean lambda is positive. Okay, so when you do set notation and go through proofs and all of that kind of thing, there's a whole language that gets spoken using symbols, and in this particular case lambda is positive. So the important point here are these dot points. The value of lambda is always specific to an interval. So if we're counting in a particular interval, we've got a lambda. If the interval changes, then we do lambda new, and we usually just write that like that, or we could have lambda b, or lambda 2 would be okay, a few different lambdas. Okay, now the probability mass function for this is given by this equation. It involves a factorial. For those of you that have forgotten about a factorial, 3 factorial is equal to 3 times 2 times 1. 0 factorial is 1, as is 1 factorial. 2 factorial obviously would be 2, and so on and so forth. But we can do some interesting algebra with n factorial. Now look at this. Expectation. What's expectation? Who can recall what expectation was? Expectation is the mean. So the mean and the variance come off these fairly easily. Okay, so let's have a look at a couple of examples of the use of the Poisson distribution. In a large corporate computer network, users log on to the system can be modelled by a Poisson process with a mean of 25 logons per hour. What is the probability that exactly 30 logons in a particular hour? So the mean process is 25 logs per hour, so that's been given. Okay, and so that'll be our lambda. So lambda, I'm just going to put it up here, would be equal to 25 logons per hour. Okay, and what is the probability that there are exactly 30? So we've got our function that defines this, which is e to the minus lambda to the power x. We don't do the proofs of this course because we simply don't have the time. Okay, so we've got our question which is asking for exactly 30 logons. Now notice the language, so I'm breaking you in gently here. The logons, okay, and okay, so you should be getting that okay. Yeah, I check it, Alex, by looking at a couple of different things, and it's telling me that that's okay. So I'm just going to keep going with it. Oh, I see. No, that's all right, mate. I'm just here to help. I can do the best I can. All right, so in this case we've got 25 logons. So every time I change something, it changes something else, which is great. Okay, so we're back to 25 logons. So that's our variable of x is 30. Okay, so 30. So x is equal to 30 logons. So we've got the probability. Now this is the part where you guys have got to start to tune in, okay? It unnerves me when people don't read the subject outline and follow that the way I've put it up, or when they don't read their folders and keep coming back asking me the same questions. It unnerves me, because then I think, well, if they can't do those admin things, how are they going to do the content? It worries me no end. But I have faith in you guys, which is why I persevere and persist, and over a long period of time we've managed to do well. What's the probability that there are exactly 30 logons? So that has a specific time now, a specific thing that you have to do. So the probability that x is equal to 30. Now that exactly reflects the question. Okay, x equals to 30. So we can use our equation. So minus lambda, which was 25, 25 to the power 30, because that was our variable x, divided by 30 factorial. Now you can practice doing that, or I can tell you that it's 0.0454, so that's 45.4 thousandths. That's the probability. So it's roughly 4%. Okay, 4% with that particular set of starting parameters. So with a mean of 25 logons per hour, what's the probability there'll be exactly 30 logons? 4%. So we're still getting used to the whole process of using our different distributions, using probability, using means, and understanding data. So we're looking through the lens of understanding data. Okay? What's the probability that there's no logon in an interval of 6 minutes? Okay, so there's a couple of issues now. So we've got our lambda, which is 25 logons per hour. So I'll put logons per hour. Then we want to say that that is 25 logons per 60 minutes. Okay, so we had to come up with that. We had to come up with that interpretation. Why did we do that? Because the interval has changed. So now we've got a new lambda. Okay, and I'm going to call that lambda subscript 6. I could call that 60 or 1 hour, but I'll just call it 6. And as a proportion, okay, it's 25. The proportion is 6 in 60. And those of you that will see that, 6 in 60. So the new lambda, or lambda 6, is 2.5 logins per 6 minutes. So there's a little bit of pre-maths that's got to be done there. So we'll get used to that idea. Then the rest is fairly straightforward. No logon. What does that mean? No logon. Ooh. That means our variable is equal to 0. So that's a trick, isn't it, in the language that we apply to our particular probability and distribution problems. So to find the probability that there are no logons, okay, what we have to do is populate the equation now. So we've got our minus 2.5 because we're using the new lambda. 2.5 raised to the power 0 still gives me 1. That term is 1. And as I just pointed out to you before, 0 factorial is 1. So you can never assume, because the variable is x with these Poisson or exponentials, that because it's 0, you're not going to get a number. So for this case, the chance that there's no logon in a 6-minute interval is 82.1 thousandths, and that approximates to 8%. So there's an 8% probability that there'll be a logon there. Okay. Alright, so what's the probability that there are between 20 and 30 logons in an hour? So we're going to have a look at the Minitab output that follows. Okay, so we'll be using that to reference it, because this is the first time that we reference data for logon. So, but we've got to write this up. How do we write this up? What does this look like? Well, let's do the probability. There's our variable. And what are we going to put around this variable? Well, we're going to say the variable is greater than 20 and greater than 30. Okay, so that's going to be the probability of x being 30, subtract the probability of x being 19. So that gives us the gap of 20 to 30. So if we go down and have a look at our chart quickly, we'll see that we can pick up these two. So 30 is 0.863, so we'll do that, 0.863309, and we subtract from that 19, and that'll give us this gap. Okay. Yes, Tyler? Yes, the answer is yes. So 0.133575, and so the probability that there's between 20 and 30 logons per hour When the question's a bit ambiguous like that, it doesn't specifically say, just assume that 20 is part of it and 30 is part of it. 7297. So there's an approximate 72% chance that there'll be log-ons between 20 and 30 in an hour. So that's using the Minitab output, and that's the kind of thing we do in the major exams when we're making it a bit easier for people. Okay, so just be mindful of that. Yeah. Okay, so we've got a couple of others to do, so let's get on with those. The example is discs. Contamination is a problem in the manufacture of optical storage discs. Now they're less popular these days because everything goes online. That was not meant to be funny, but I know it was. Irony. So the number of contaminated particles that occur in an optical disc follows a Poisson distribution with a mean of 0.1 per centimetre squared of media surface. So we've got to think about lambda here with respect to area. The area of the disc under study is 100 centimetres squared. Find the probability that we observe 12 contaminated particles. So for our setup, we just need to follow the setup, and so we've got a distribution, and find the probability that we observe less than 12 contaminated particles. Okay, so this should be fairly straightforward. So in here we can write the probability of x being less than 12 is equal to, now this is the distinction I think Tyler was asking me before. So we'll include everything up to and including 11. And in doing that, we cover the less than 12 proposition. Less than or equal to, it says less than explicitly. Okay, so we can read that off, and we can read that directly off our printouts. So 0, that's the previous one. Okay, so I'll just do that. Zero 0.696776. Okay. All right. The next thing we want to do is find the probability that we find more than 6, but less than 15. More than 6, but less than 15 contaminated particles. So we put together our interval, and we've got greater than 6 and less than 15. So we'll take the first 14, which takes us up to the boundary of 15. And you'll notice I'm manipulating this so that I can always use this inequality. Okay? And we'll subtract the 6, because 6 is not included. So we'll get all the difference between 6 and upwards, 7, 8, 9, 10, 11, 12, 13. Less than 6. And so we'll get, this one's 0.9165. 42. Subtract 1301. And so we get an equal of 78%, 786. So approximately 78%. Okay. Now suppose that there's a smaller disk. So in this case here, as somebody's already pointed out, lambda is 0.1. However, we're scaling that 0.1 now to the 40. So that means we'll get 4 errors per 40 centimetres squared. And so the probability that we observe fewer than 2, so there's that language again, fewer than 2, means that we've got to write the probability of x being less than 2, which is all of 1, less than and equal to 1. So that's our CDF, isn't it, when we do it like that? And that's 0.0 915. Okay, we can. I'm just doing them that way at the moment, just to give you a feel for what's happening with those. Okay. Now we'll have a look at probability distributions and probability density function and continuous random variables. We'll have a look at those, but at the moment we've just got another one of these to do. So you might have wondered where I got all the p-values from. Sorry, I should have mentioned that before. All of these p-values are being read off these tables. So where the mean is 10 for the original problem, we pick off each of those, and where it's 4, we pick off each of those. Okay. Okay, so let's have a look at this one. So the area of the disc so we've got with a mean of 0.1 and the area of the disc is 100, find the probability that we observe 12. So let's put the data together. 0.1 errors per centimetre squared. So that's, now this is the bit that's interesting, 0.1 per times 100, because it's 100 per centimetre squared. Is equal to 10 per 100 centimetres squared. So for P is equal to 12, we observe 12 contaminated particles. Px is 12. And we've got e to the minus 10, 10 to the 12, divided by 12 factorial. And if we put that through the computation, we'll get this number here. So there it is printed out. It's the same calculation, right? So that's the same calculation. So we'll get 0.094. Now I would normally go for 3 SIGs, just like that. Obviously you'll get more with, depending on which software package you use and what the parameters are you set it up for. So that's fairly straightforward. Alright, so when we look at this question, somebody's asked about the lambda being 0.1. That's the clue. The mean is 0.1. The mean is 0.1. So okay, so I don't know that I wrote it out entirely, but I did last week, and I'm just doing this again. The mean is there. And so when we read the question goes to say, alright, what's the question saying? The mean of 0.1 per centimetre squared. So it came from the question. Okay, it just came from the question. That's all. Just came from the question. Okay. So sorry, I've just got to keep track of where I'm at. So that's pretty much an example of what's happening with our Poisson distribution. I'm just thinking to myself, that's a fairly rudimentary run through, just picking the values, using them together like that. So we'll do a more challenging example. So we'll do this Poisson distribution challenging example. So this highlights the word issues related to statistics. The word issues related to statistics are very significant. And this is an example. Now, I'm not going to cruel you with an exam question that is like this, but this could be an assignment question, for example. But let's work our way through it, because I'm very conscious that for many of you this is still a very new area. Suppose cars wish to pass straight through an intersection from north to south and arrive at an intersection at an average rate. Now there's a bit of misleading language right there. That's our mean, 1 car every 10 seconds. So 1 car every 10 seconds. So that's our first piece of information. So we can take from the question lambda is our average, okay? And what that means is that we can have 1 car every 10 seconds. Now, how do we translate that any further? We might have to scale that depending on the nature of the second part of the question. So let's read on. Suppose the cycle of lights are timed in such a way that these cars must wait 2 minutes at the intersection before being given a green light. Okay, so the average rate of a car is one every 10 seconds, but then the question's posing they have to wait 2 minutes for the intersection before they get a green light. Suppose that 15 cars could clear the intersection in this direction each cycle. What is the probability that at least 1 car that had stopped at the red light will not pass through the intersection in the next green light if there are no cars waiting at the previous green light? What? Okay, so we can actually do this. It's a bit tricky, but we can actually do this. Now, again, I'm not being a smarty pants. I'm not giving you ones that I'm going to worry you about, but I need to show you guys, right? You develop a bit of a passion for this stuff, and you can make it happen. Now, the other way of viewing this 1 car every second, now that we've changed contexts, is that we can actually we can actually view it in terms of there. Just push that up. Sorry, I'm playing. I know I'm playing. I do take it back. So we can just do that in terms of this 2-minute cycle. So what can we do in terms of the 2-minute cycle? Well, if it's 1 car every 10 seconds, then there's 6 blocks of 10 per minute. So in 2 minutes, there's 12. So what we can convert this to, we can scale this by saying 12 cars, okay, every 2 minutes. Okay, 12 cars every 2 minutes. So they're the same thing. Okay, so we could write equals 12 per 2 min, or something like that. Okay, we could write it like that. But we're getting closer now, because basically we get to answer the question. What's the probability that at least 1 car that had stopped at the red light will not pass through the intersection at the next green light if there are no cars waiting after the previous green light. So what that means is that if they come to an intersection that's empty, what's the probability that when it's waiting at the red light behind other cars, provided there were no leftovers from the previous cycle, what's the probability that there'll be no cars waiting? Because that's what you want to do as a designer, don't you? As an engineering designer of intersections, and this is traffic engineering, okay? So in terms of traffic engineering, we want to clear the intersection. That's the thing that we would like to do. So we would like to have at least one car stopped. So we want the probability is going to be that our variable is greater than 15. What's the probability that will clear the intersection? Greater than 15. Okay. What would be the probability of the 16th car being stuck? Okay. The 16th car not passing. So I know it's interpretative, I understand that, but this is the nature of real world problems, and this is why you guys are in the top now, a few percent of employees when it comes to problem solving, because of your engineering prowess, and the maths is helping you develop that. So just be patient with me, be patient with the course, you'll get there. This is a challenging example, and I'm doing it deliberately to expose you. Now come on, you've seen the practice mastery test, you know it's not as hard as this, but we've got to deal with stuff like this. It's part of our education. Alright, so how do we reverse this inequality sign? Would anybody like to offer me something? How do we reverse the inequality? We did do it. I'm just wondering if you've forgotten. You may have forgotten. Okay, we take the complement. And when we take the complement, and I gave you a clue there by writing that 1, you can do this. Yes, thank you. The 16th car would mean that we want to clear all 15 cars. So then we can go back up to the table and we can pull this 1 out and we'll get a total of 0.15. So the probability that there will be no cars waiting after a previous green light so that 15 cars is about 15%. So that approximates to 15.5%, 15.6 if I do it like that. Okay, so that's an interesting way of looking at those. So this was about count. Poisson distributions are about count. Just keep that in mind. Okay, and the interval is something that we'll have a look when we return next Thursday and we go back to stats and maths separate ones. Okay. Alright, what I'm going to do is I'm going to change up now. So I'm just going to have a 1 minute change and then we'll come back. Okay, so just give me a moment just to bring this to your attention. Okay, I'm nearly there with you. Okay, so that's good. Alright, so I'm going to take this one away.